Welcome everybody. We've spent a lot of time looking at integration and not as much time looking at examples, right? We've done things very theoretically. So I want to apply a lot of the techniques we've been using to a specific function, but not a typical function. Okay, so this is one of our monster functions, and it's called Thomaes function. And we're actually, before we even do some integration, we're going to talk a little bit about limits and continuity, and then we'll actually get back into the integration. So first, let's define the Thomaes function. And before we even do that, just a little bit of sort of ad hoc terminology. So if I have a rational number q, then I know I can write this number x, say, as a fraction. So I could write x is equal to m over n, where m and n are integers. Of course, we know that the denominator should be non-zero. But if I want, I could always just assume even that the denominator, and let's call it n here, is positive, right? Because if x is positive, I could just, if there were negative m over negative n or something, right, I can drop the negatives. If x is negative, then I can put the negative either in the denominator or into the numerator, and let me just assume if it is negative, I put it into the negative into the numerator. So I'm going to assume here that n is positive. But also, it could be that m over n looks like something like, I don't know, 4 over 10, in which case I could reduce it to 2 over 5. So I want to assume it's reduced. So I'm going to furthermore assume that the greatest common greatest common divisor of m and n is equal to 1. Okay, so this is just basically telling me that n over n is reduced. Okay, and once I have all these conditions, this is a unique representation of x, right? So if I want to write a rational number as a fraction, and I make the denominator positive and I reduce the fraction, that right there is unique. There's only one way to do that. So that's pretty cool. This n then completely depends on the x that I choose. And so I'm going to call n the reduced denominator of x. And because it would be convenient when somebody just gives you an x, you want to say what is the reduced denominator of x, I'll even come up with some notation. I'm going to call this r of x. So n, the denominator, the reduced denominator, will just be denoted by r of x. So for example, if I have something like, I don't know, well, how about our 4/10? And I say, what is the reduced denominator of 4/10? The reduced denominator would be 5, because 4 over 10 reduces to 2 over 5, and the denominator is 5. Okay, fair enough. So now let's define Thomaes function. So this is going to be a function, well, we could define it on all real numbers. Although when we talk about integration, for example, we'll just restrict ourselves to like 0, 1, but it doesn't matter. We can define it on all real numbers. And what it's going to do is, if my input is rational, then I'm going to send x to 1 over its reduced denominator. Okay, so if I had t of 4 over 10, this would be 1 over 5. Right? Whatever, it doesn't matter what the numerator is, right? I just turn it into a 1. It's probably useful to note, okay, what happens with 0? Well, the reduced fraction for 0 is 0 over 1. Okay. Of course, I could use any denominator I liked, right? 0 over 5 is also equal to 0. However, the GCD of 0 and 5 is 5, right? 5 divides both 0 and 5. So this is not going to satisfy our assumptions here. So 0 over 1 is the only one that does. And then we just use this same definition, this would be 1 over 1, which is 1. Okay, now of course x doesn't have to be rational. It could be irrational, in which case the function just returns 0. So this is what we call Thomaes function. All right, and so what is going to be quite interesting about Thomaes function is that Thomaes function is discontinuous. It's discontinuous a lot, right? Not at every point, but at precisely the rational numbers. So our first claim is that t is discontinuous on Q. So if I take any rational number, t will be discontinuous at that rational number. All right. This actually turns out to be very easy if we use the sequential characterization of continuity. So you'll recall when we talked about continuity the first time, we had the sequential characterization which said you are continuous at some point A, if and only if every sequence in the domain that converges to A has the property that its F image converges to F of A. All right, so if I can show that this fails, then my function is not continuous at A. All right, well, let's let A be a rational number. And I know that by the density of the irrationals, I can find a sequence of irrational numbers that converges to A. So by the density of the irrationals, there exists, let's call it x dot, an I sequence x dot such that x dot converges to A. Okay, but what happens when we apply t to x dot? Well, Thomaes function takes all irrational numbers, sends them to 0. So this is just the 0 sequence, which converges to 0. On the other hand, what is t of A? Well, t of A is a rational number, so this will be 1 over the reduced denominator of A. Well, the reduced denominator of A is some positive number. 1 over it is some positive number. So this tells you t of x dot does not converge to t of A, and therefore t is discontinuous at A. Oh, wow, that was a pretty easy proof. Okay, well, what about on the irrational numbers? Is t discontinuous there? Actually, it turns out no. Our second claim is that t is continuous on all of the irrational numbers. All right, so this one's going to be a little more challenging than showing that t is discontinuous on the rationals. Nice thing about showing discontinuity is you could use the sequential characterization, just find one sequence that doesn't do what you need it to do, and you win. But for continuity, right, we're going to actually have to do a little bit of work here. So let's let, well, I already used A, so let's let B be an irrational number. Okay, and we're going to show that t is continuous on B. Okay, so what do we need to show, right? So we need to show that the limit as x approaches b of t of x is equal to t of b. And what is t of b? Well, b is an irrational number, and Thomaes function is 0 on all the irrationals. So t of b is 0. All right, so that's not too bad. We need to show that the limit of this function is 0. Fine. If we're trying to show a limit of function to 0, that means for all epsilon something, something, something. So let's let epsilon be greater than 0. Now, by the Archimedean property, we can find some natural number n such that 1 over n is less than epsilon. So by the Archimedean property, there exists a natural number n such that 1 over n is less than epsilon. All right, now here comes the clever bit. I'm going to define a set. I'm going to call it big B, because, hey, I got a little b. That's going to depend on this n. So B of n is going to be a set. All right, so let B of n denote the set of all reduced fractions and I'm going to take them in, it really doesn't matter a whole lot. I'm going to take them between b minus 1 and b plus 1. So this is a b coin of radius 1. And, well, there's a lot of reduced fractions in there, but I'm going to restrict it just a little bit more. I'm going to say with denominators less than n. Oops, less than n. And this is going to be a much smaller set. In fact, B of n is going to be a finite set. And that may not be obvious at first, but let's talk about why that's true. So B of n is finite. So the first thing you should be thinking of is, well, all right, there's only a finite number of denominators less than n. Okay, so that's the first thing. Only a finite number of denominators less than n. So I don't have that many choices, right? I have n minus 1 choices for denominators. And what can I put in the numerators, right? Well, seems like maybe you could put a lot of things in the numerators, but this restriction that they have to lie between b minus 1 and b plus 1 actually closes things down a bit, right? In fact, so it's the first thing. Second thing, if k, say some little k, is less than or equal to b minus 1 times our n, and or let's say actually just take any denominator, right? So if I have a denominator, right, less than n, so here n, little n will be less than big N. So if k is less than or equal to b minus 1 times n, and if little l is at least b plus 1 times little n, then k divided by n is going to be less than or equal to b minus 1n over n. Okay, I just replace the k with b minus 1n. But this is equal to b minus 1, which is less than b plus 1, which is equal to b plus 1n over n, which is less than or equal to L over n. Okay, and so what's the point of all this nonsense? Well, the point is that if I have any number k, which is less than or equal to b minus 1 over n, then I'm getting a fraction which is outside of this interval b minus 1 to b plus 1. And if I have a fraction, L over n, where the L is at least b plus 1 times n, then I'm again getting a fraction which is outside of this b coin of radius 1. So the only fractions that I'm going to have in this set B of n are ones where the denominator is less than big N, and the numerator is going to lie in between b minus 1 times little n and b plus 1 times little n. And that's a finite interval. Okay, so this B of n is a finite set. Now, because it's a finite set, if I sketch b minus 1, b plus 1, B of n they live somewhere in here, but there's only a finite number of them, right? Okay, there's b somewhere in the middle. Okay, b itself is not in B of n because b is irrational. But I know I have some finite collection of these somewhere in here. Who knows? They lie in there somewhere. But at some point, I have to stop drawing these dots. And when I do, I can build another B coin, which is so small that it doesn't contain any of them. So since B of n is finite, there exists some delta, okay, so delta will be the radius of this B coin. There exists some positive delta such that this B coin of radius delta does not intersect this collection of reduced fractions with denominators less than n. Okay, now let's say I work inside this interval now, right? Which, by the way, why am I trying to do this? Well, remember, I'm trying to show that t is continuous at b. So that means for all epsilon, I need to find a delta. Hey, there's a delta, such that if I apply the t image, or if I apply t to this b coin, I end up in the 0 coin of radius epsilon. All right, well, so that means we need to apply t to everything in this interval. All right, so we're going to apply t to this interval. Now, there are two types of points in this interval. There are rational points and there are irrational points. So if x is a rational number, right, which is, well, I should say, let's make sure we're saying it's inside this interval, right? So it's in Q, but it's also in this interval. Then what can I say happens when I apply t to it? Well, I know that r of x is at least n. Why do I know that? Well, the reduced denominator of x cannot be smaller than n, because we know that inside this little red B coin of radius delta, there are no reduced fractions whose denominator is less than n. Okay, that was the whole point of what we did up above. All right, so we found all of the denominators that were small meaning less than n, and we're getting rid of all those fractions. So the only thing left are going to be fractions whose denominators are big meaning at least n. So the reduced denominator of x has to be at least n. But if that's true, that means that t of x, which we know is equal to 1 over the reduced denominator of x, is less than or equal to 1 over n, and 1 over n was less than epsilon. Hey, that was our that was our goal there, right? Okay, now that's if x is rational. What if x is irrational? Well, that's the easy part, isn't it? If x is irrational, then t of x is equal to 0, which is certainly less than epsilon. So what we can conclude is that if I apply t to this B coin of radius delta, it completely lies between negative epsilon and epsilon. In fact, it lies between 0 and epsilon, right? But this is good enough. So this implies t is continuous at B. But we're not done yet. Okay, we've proved our claim, but there's more we want to talk about, right? I want to talk about integrability. Is Thomaes functions integrable? Okay, is it integrable? So we're going to restrict ourselves to a particular case, but this particular case is not particularly special, all right? So we're going to restrict t to, say, the interval 0 to 1, just for simplicity. And we want to ask, is t integrable? And if the answer is yes, then this actually would be a little bit surprising, because we've already proved that if you have a continuous function, it is integrable. And if you have a finite number of discontinuities, then it's integrable. But this is a totally different ballgame, right? T, we just discovered, is discontinuous on all of the rational numbers. That is a countably infinite number of points. So it seems at least a little far-fetched that t could still be integrable. And yet that is exactly what we're going to show happens. Okay, so the answer is yes, yes it is. Okay, so how are we going to prove that? Well, I want to use the integrability criterion, right? So we're going to take an epsilon, right? And we're going to show that I can find a difference between an upper and a lower sum that's less than epsilon. Actually, it's a little bit nicer than that. Before we jump too far into any of the deep stuff here, let's just make a little observation. What if I was trying to compute the lower sum of t on some partition? Okay, so W here is just some partition of 0, 1. Who knows which one it is? Well, to compute this lower sum, I would have to, well, let's see, look at something like this, right? It'll be a sum, I don't know, say it's got n, it's an n partition. I'm looking at the infimum of t applied to all of the different intervals multiplied by the length of the intervals. Okay, but in every interval ik, okay, so in every ik, there exists some x in the irrational numbers. This is, again, the density of the irrationals at play. But if you apply t to x, you get 0. So, of course, there's nothing smaller than 0 in the image of t. So the infimum is actually going to be the minimum of t. This is going to equal 0. Okay, well, it doesn't even matter what you multiply by in terms of the lengths. You're going to get 0, 0, 0, add them all up, you still get 0. So no matter what partition we use, the lower sum for t is going to be 0. So when I want to use the integrability criterion, I'm actually in a nicer situation. I only have to show that the upper sum can be made as small as I want, right? I just need to get the upper sum less than epsilon, or maybe some positive multiple of epsilon. Okay. So that's the game plan. All right. We need to just focus on the upper sum. So let's do that. Let's let epsilon be greater than 0. Fine. We play the same game again as before by the Archimedean principle. There exists some positive integer n such that 1 over n is less than epsilon. Okay, now I'm going to use essentially the same game as I did up above. I'll change the notation just slightly so that we don't think it's the exact same b of n, but let's let a of n, okay, same idea, be the set of all reduced fractions in 0. Well, how about I'll let it go up to 1. Doesn't matter a ton. With denominator less than this n. Okay, so I'm going to get positive fractions who are less than or equal to 1, but denominator less than n. So again, just as an example of what we're talking about, let's say we figured out that the n was equal to 5. In that case, my a, this a of 5, this would be all of the reduced fractions whose denominator is less than 5. So I could have 1 over 1, I could have 1 over 2, 1 over 3, 2 over 3, 1 over 4. I don't get 2 over 4 because that's not a reduced fraction, but I do get 3 over 4. And then I could have nothing, right? I already have 1, and I can't have anything bigger than 4 in the denominator. So there you go. That's all of it. Okay, so that's what my a of n is going to be. Okay, and now I'm going to choose a partition, right? I need to get some partition, and here's how I want to choose it. So choose some partition, I don't know, we'll call it x this time. So we have a partition of 0, 1. And it's going to be, I don't know, we'll make it an n partition so we can keep track of this, such that Well, what I want to do is make sure that none of the individual parts of this partition, right, the subintervals, are very big. I want them all to be reasonably small. And of course, I can always do that, right, well, if I had 0 to 1 and you don't like the partition that I had, right, you think, oh, maybe these are too big, I can always just cut them in half, right, by adding more points. So I can always make these partitions smaller and smaller and smaller. And so I'm going to do it such that if I take the max, okay, over all of the different intervals, okay, so I'm going to take the max of the lengths of these intervals, I want this to be less than epsilon, and then I'm going to actually scale it even down a little even further. I want it less than epsilon over the cardinality of A of n. Now, it's not obvious why I'd want to do that at first, but you'll see what's going to happen here in a second. Okay. Now we need to make a little observation. So I'm going to write this observation here. Oops, I wanted this in green. A little observation. I'm going to leave a little room actually for the observation because I want to start writing down the upper sum, and then we're going to come back to this observation. So if I try to write down the upper sum for t on this partition x, I know this will be, okay, a sum, k goes from 1 to n. I'll be computing the supremum of t on this interval ik, and I'll be multiplying by the length of ik. Okay, so I'm interested in the supremum, which means I'm not so interested in the irrational numbers anymore, because I know the value of t on those is all 0. I'm actually interested in the rational numbers because t of those will be positive. And since I want the supremum, right, I'm looking kind of the largest one I can get. Now, I'm trying ultimately to get my upper sums tiny, right? I want those less than epsilon. So having big supremum is not really good for that cause, right? That does not help us. So what am I worried about? I'm worried about getting these fractions, right, that are the so-called big fractions, right? The ones in A of n, those are the ones with the smaller denominators and hence are bigger fractions. So I'm kind of interested in how often, right, in the worst case scenario, how often can those show up in my partitions? Okay, so let's actually do an example with A of 5. So I'm going to redraw here my 0, 1. And of course, well, 1 over 1, that could be right there. And 1/2, okay, that's in the middle. 1/3, let's say that's about right there. 2/3, okay, that's going to be on the other side. There's going to be our 2/3. 1/4, okay, there we go, 1/4. And then 3/4, okay, maybe that's about right there. All right, so the worst case is if when I write down my partition x, is if the big fractions occur right on the boundaries. Because if they occur right on the boundaries, what's going to happen when I try to say, let's look at this first interval, right? So say this is our I1. When I look at the supremum of t of I1, well, 1/4 is going to be the rational number with the smallest denominator and hence the highest value. And so the supremum of t on this first interval is going to be 1/4. And if I move over into the next interval, and even if I cut it off to get rid of this 1/3, that 1/4 is still there. It shows up in both intervals because it's on the boundary. So that feels bad. Okay. But that's just something we have to deal with, right? We have to figure out how often could these big, bad fractions show up. And so this is our observation, right? The observation is that at most, twice the number of points in A of n, okay? Because each of these can show up twice, once on the left, once on the right. So at most, 2 times the cardinality of A of n intervals intersect A of n, right? Can contain points from A of n. And that's going to help us when we break this down a little bit further to put some upper bound estimates on how big this upper sum can be. Okay, so what I'm going to do is I'm going to break this sum up into 2 pieces. There are intervals that contain these bad fractions, meaning they intersect A of n, and there's intervals that, well, hopefully don't. So I'm going to sum up those separately. So our first sum, these are going to be all of the ik's that do intersect with A of n. So that means that their intersection is non-empty. And I have the supremum, t of ik, times the length. Plus, now I'll get the sum of all ik's that do not intersect A of n. So this intersection, this intersection is empty. And it's the same supremum, t of ik, times the length of ik. Okay, now, this supremum here, I know in the worst case scenario, right, is I have the 1. Now, most of the intervals are not going to have that, but that's okay. I'm just going to replace this with the worst case scenario is that the supremum was 1. So I know that's less than or equal to 1. Also, I know from up above that I've chosen a partition so that all of the lengths are bounded. In fact, they're less than epsilon over the number of points in A of n. So I can say that this length is less than epsilon over the length of A of n. Okay, and now let's check the other bit here. Well, it looks to me like this supremum, since I'm looking at things that do not intersect A of n, the absolute worst case is that I get a fraction like 1 over n, 1 over big N, right? Because I know I don't have anything with a smaller denominator. So this is the worst case over here. These are all less than or equal to 1 over n. But now 1 over n, where did that come from? Ah, yes, the Archimedean principle. We said we could find some capital N such that 1 over n was less than epsilon. Ah, so this here is less than epsilon. All right. I could say something here about this length, but I'm actually just going to leave that alone for a moment. We're going to get that back to that in a second. Now, what's happening over here? Well, here I have something less than or equal to 1 times something epsilon over A of n. Of course, this is non-negative. So when I multiply these, this is going to be less than or equal to epsilon over the number of elements in A of n. Okay, but how many of these things am I adding up? Well, how many intervals intersect A of n? And that's where the observation comes into play. We know that at most 2 times the number of points in A of n intervals intersect A of n. So I'm getting at most 2 cardinality of A of n copies of this number. So in our next line, we know this is going to be less than, well, I should have said less than here, right? Less than or equal times less than is less than. This is going to be less than 2 times the number of points in A of n times epsilon over the number of points in A of n. Ooh, that's pretty good because those A of n's are going to cancel. This is why I wanted this divided by A of n. All right, now we have plus. So what happens here? Well, we know that each one of these suprema is less than epsilon. So I can replace, or I can pull this epsilon out. And so this piece up here will be less than epsilon times the sum of the lengths of the ik. Oh, well, what's the absolute worst thing I could get if I added up all the lengths of all the intervals? Well, that would just be 1. This is less than or equal to 1. And so this piece is less than epsilon. So I get an epsilon here. Okay, well, we get a little cancellation going on, and then I'll have 2 epsilon plus epsilon, which is equal to 3 epsilon. And so what we've just shown is that the upper sum for this partition is bounded by a positive multiple of epsilon. And so by the integrability criterion, T is integrable. Oh, that's pretty cool. All right, so we have now shown that it is possible for a function with a countably infinite number of discontinuities to still be integrable. It turns out that that will always be the case. All right, so maybe down the line I'll put another video up where I prove that in general. We're going to move on, actually, because I want to show you what happens when you even have an uncountably infinite number of points of discontinuity. You might still be able to get integrability, but you're not always going to. Now, to show that, we're actually going to do one more characterization of integrability. It's called the sequential characterization, of course, right? We had to have a sequential characterization. So we will see that next time.